Alright guys, good afternoon. Today we are going to do a video on this worksheet, and this worksheet only, the Chapter 16 practice. I've had a bunch of people ask me questions, and rather than answer all the questions individually, it will take less time for me to just do a video on all the questions, and yeah, so here it is. Alright, so number one asks for what, if delta H for a reaction is 25 kilojoules and delta S is 5.0 joules per Kelvin, at what temperature range is the reaction spontaneous? And then the same question with these numbers. Alright, so we know that we're going to use this equation. We're going to use the delta G equals delta H minus T delta S equation, and I should have a little thingy on there, because that will tell us whether or not the reaction is spontaneous. If delta G is negative, then the reaction is spontaneous, like you see. So we can substitute the values in that the question tells us, the 25 kilojoules, and we have to change that 5 joules per Kelvin into kilojoules, so we move that as point over 3 times. Temperature we don't know, but we know if this thing is negative, if delta G is negative, then the reaction is spontaneous. So 0 will tell us the boundary between those. So if we solve for T, here, we get 25 over 0.0050 kilojoules per Kelvin, and kilojoules cancel out with star per Kelvin, and we get 5,000 kilojoules. Now remember, if delta H is 25 kilojoules, that means it's an endothermic reaction, which means it's going to be spontaneous at higher temperatures only. And so we want to maximize this. If this T is bigger, then this will be more negative and this will be more negative. So it's spontaneous over 5,000 kilojoules. 5,000 is the minimum number to make this entire thing 0. And if this number is bigger, that means it'll be less than 0, so it's spontaneous over 5,000 kilojoules. You could also do this with an inequality, but you don't really need to. All right, so the same thing for number 2. Number 2 is the exact same, only you're using different numbers. So we have 0, we have the negative 10 kilojoules, and the T equals negative, and we again had to change that to kilojoules from the second one, because that was 40 joules per Kelvin. So we set it equal to 0, we solve for T, and T here was 250 Kelvin. But again, remember, if delta T is negative, that means that it's an exothermic reaction, so it's only going to be spontaneous at lower temperatures if the delta S is also negative. So spontaneous under 250 Kelvin, and the sig fig should have been probably 2 sig figs on this first one, so that 5,000 should have ended there, and also the 250 should end there as well, but yeah. Okay, so that's numbers 1 and 1a. For 2, for ammonia, the enthalpy of fusion is 58.51 kilojoules per mole, and the entropy of fusion is 28.9 joules per mole Kelvin. Now this one, we're going to get a really big number that is not actually the melting point for ammonia, because when I wrote this number down right here, I wrote it down wrong, and it actually should have been 5 point something. It should not have been 58, but so we're going to get a number that's like 2,000 some odd when it really should have been 200, like 208 Kelvin, which makes sense because ammonia is liquid at room temperature and freezes at some slightly lower temperature, whatever. So we're not going to get the right value for this, but still we can show you how this could be done. So for 2, we would use, so we have the delta H of fusion is 58, and so the arrow there indicates, yes, I effed up on that. That number should have been like a factor of 10 off. Delta H of fusion and the delta S of fusion is right here. So again, we substitute those into our delta G. The delta G equals delta H minus T delta S equation, because we're again talking about spontaneity. So if we're talking about spontaneity, we have to use that equation. So we again solve for T, and the T we get here is 2,024 Kelvin, which is way bigger than it should be, but blur. All right. So next one, number 3. For number 3, it says the delta S for the following reaction is negative 358 joules per Kelvin, and it gives us the reaction. So the first thing we need to do, which I actually forgot to do the first time I did this, is balance. We need to balance the reaction. So we got 2 carbons and 1s, which